4. We're pretty much towards the end here of this chapter. We have one more example to go. So I'm just going to finish this chapter up. So just keep us on pace and all that good stuff. And then afterwards, we'll talk about part 2 of the experiment today. And then you can continue on with the buffer experiment and all that good stuff. Okay, so we've now gone into sort of talking about complex ions. And again, as we talked about a little bit earlier, complex ions are essentially metals that have these Lewis bases attached, which are referred to as ligands. And when we have those complex ions that get formed, they typically do have a fairly large value of K. So the Kf values are typically very large values. And what that usually means when we sort of approach these type of problems is we make really kind of two assumptions. And what we did in these last two sort of examples is the first really assumption is because the Kf value usually is relatively large, that means that in these type of equilibriums, really the equilibrium it falls really far to the right towards the products, and that's really towards complex ions being formed. So what we assume is because in order to form that complex ion, you need that metal to be the kind of the center of it. All of the metal is going to be used up in this process where we form complex ions. Whatever the individual metal ion is, it's going to be used up to form this complex ion. So what that allows us to do is, as we did in our first ice tables or so, is to make the assumption that the change part is really going to be the metal. So we essentially use all of the metal up and we basically zero it out. And what that allows us to do is basically figure out the equilibrium concentrations of our complex ion. We could also figure out the equilibrium concentration of our ligand. But keeping that in mind that it is truly an equilibrium, even though that almost 100% of that free metal ends up in that complex ion, there is going to be some of it coming back the other way, and you are going to have a very, very small amount of the free metal still available to you in the solution. And that's sort of the second part of the assumption is if we assume that the metal is zero, when we actually do go back and solve for the free metal that's in that solution, it should be a relatively small value. And as we saw here in the one we're looking at, this was like to the minus 18. I think maybe the other one was minus 15, something like that, 13. It's a very, very small amount. I mean, it's pretty much not there, but technically speaking, it is there, and to that small amount. So one way you could kind of check yourself to make sure that you didn't necessarily mess up a calculation that involves this is to, if you see that when you do solve for the free metal, it's a really large number, then something definitely went wrong. So again, should be a really small number when you do solve for it. Now, what this example that we just did sort of showed us is we have these stepwise formations happening of this complex ion. And because each of those steps are essentially equilibrium steps, we could use each step individually basically to solve for what we needed. So in this particular example, we wanted pretty much everybody's concentration at equilibrium. And because we have these kind of individual steps in this equilibrium, we were able to use those individual steps to help us find, what we were looking for. So, for example, obviously, the first after the first table, we had both of these guys, so we could use that second step by itself to figure out this guy. And then after doing that, like we saw, we had both of these guys, and we could use again that first step independent of everything else to figure out what we had going on in terms of the silver concentration. So that's one approach where you could use both of those things just like we did. The second approach would have been to actually, let's see here, would have been to do this first table like we did here. So I'm just going to kind of take this first table here and sort of copy it over. And this was the overall reaction. So this was the overall reaction, which was basically this guy. plus a couple of these guys. And it made our that was 3 minus, I believe. So that was our overall reaction that we had here. And you remember we got that overall reaction from adding both of these steps together. Now, if we added both of these steps together and we wanted the Kf for this guy, it would be K1 times K2. So we could actually get the Kf for the overall reaction by multiplying these two values together. And if we do that, that is 7.4. You get the clear. There you go. 7.4 to the old 8 times 3.9 to the 4. That gives us something like 2.9 to the 13 would be our K value for the overall reaction. And we could use the combined K value there. And I'll just rewrite it here. So the Kf for this guy, by taking both of those K values together, gives us something like 2.9 times 10 to the 13. So an alternative approach to going back to each of the individual reactions like we did is after we did this first ice table here, you could use the combined K value and solve for silver like we did in the first example. So if we did that, our K here would be divided by our silver, and our S2032 minus squared equals 2.9 times 10 to the 13. Putting in our numbers from our very first ice table, so this number here and this number here, we're going to basically solve for silver, very much like we did in the first example. So it'd be good if I remember those numbers, 4.29. So we have 4.29 times 10 to the minus 4, our silver, and this guy was 2.86. We're going to square it, equals 2.9 times 10 to the 13. Again here, basically the silver and the Kf are going to switch places. That means the silver is equal to 4.29 times 10 to the minus 4 divided by 2.9 times 10 to the 13, and our 2.86 squared. So at this point, if everything went right here, hopefully it will, we get 1.8 times 10 to the minus 18 molar, which if we look above is the exact same number we got by going through each of the individual sort of steps. So an alternative approach, like I was talking about at the beginning here, is you could have used the combined equations and used the overall combined reaction like we did in the first ice table. And after that first ice table, you could have went into the equilibrium constant for it and solve for silver first, and then work your way backwards, to solve for, something else that it would be missing, the third guy that would be missing in that particular case. Any questions on that there? So again, a couple different ways you could kind of do this depending on, sort of which route you take. They all technically should get you to the same spot because they are all technically equilibriums. So for example, if I did this, I could have then went in to the top one here and we use my silver and this guy and solve for this guy. So again, it's a couple different ways that you could kind of approach it. They all should end up with the same answer, regardless of sort of which approach. Question on sort of that alternative way where we use the combined K value. And again, you could check that if you take, if you were to do that, if you put the silver we just got into here, plus our 2.86, our times our 2.86, and then times it by this, you get this number. So again, you could have went to silver first and then went backwards, or did it the way we did, where we waited and did silver at the end using each step. Any questions on any of those steps there? Okay, so one last sort of complex ion sort of problem here. So we saw one where sort of a straightforward complex ion problem. We see one here where we have more of a stepwise fashion. And now what we're going to look at is sort of a combination of the couple of Ks that we talked about here in this chapter, putting together sort of our KSP and our KF together. And sometimes that happens because sometimes we do have to combo some of those things. So looking at our next example here, we want to calculate the molar solubility of silver chloride in a 1 molar solution of ammonia. So basically we want to know, is it soluble? What is the solubility of silver chloride if we dump some ammonia in it, not water, but in actual ammonia? So we have two equilibriums here. We have our KSP equilibrium, right, which deals with solubility. So we have our silver chloride going to our silver ion plus our chloride ion with our KSP of 1.6 times 10 to the minus 10. We also have our complex ion formation here, excuse me, which is the silver ion plus the ammonia, making our complex ion. And we'll know how to name that later on in a different chapter. And that's our KF. So really in this reaction or this sort of problem, we're really wondering what happens when we kind of do both of those things, kind of mix those things together. So where we might want to start with is adding both of these together and seeing what we come up with in terms of an overall reaction. When we do that, the silver ion is actually going to cancel each other out. And we actually do get kind of what the question is asking. If we take some silver chloride and we react it with some ammonia, what will be its solubility, which will look something like this. So this is basically the overall reaction that's taking place. This is also really, what it's sort of saying. We're taking our silver chloride, which is a solid. We're going to add some ammonia to it and kind of see what happens. So because we added both of these reactions together, we want a K value for this overall. So you may be asking yourself, can I take a KSP and can I times it by a KF? And the answer is yes, because it really doesn't matter what the little symbol is on the bottom. They're all the same. They're all equilibrium constants. They're all products over reactants. You could multiply Ka times Kb like we did. You could multiply Ksp times Kf. It doesn't really matter. You can multiply different types of equilibrium constants together because ultimately they're all really the same thing. They're all really products over reactants calculated the same way. So in this particular case, we would multiply those K's together. Again, a reminder, when we add equations together, we multiply the K values, not add them. So we want to multiply these K values. And if we do that, we get 1.6 to the minus 10 times 1.5 to the 7, I think. That's going to give us something like 2.4 to the minus 3. So this is the K value for kind of the overall reaction that's taking place when we take our solid silver chloride and we mix some ammonia in it. And we get this 2.4 times 10 to the minus 3. So what we want to focus in on at this point is really the overall reaction. So if we focus in on that overall reaction, again, from adding those guys together, we get our silver chloride plus our ammonias, making our complex ion. And again, our K here going to be 2.4 times 10 to the minus 3. Now, we're not interested necessarily in the concentration of our complex ion. We're not really interested in our ammonia. We're really interested in the molar solubility, our molarity of our silver chloride. So we're really looking for its solubility. So the way we would want to approach this reaction here is we would want to do an ice table more in the line with our KSP tables. So we're going to do really a KSP table here. And we're going to start with what it was given to us. And in this particular case, it wanted to know what is the solubility of silver chloride in 1 molar ammonia. So we do have the starting amount given to us. We don't have anything on this side, so we'll do our zeros kind of like normal. We're going to do minus 2s again because of the 2. This is going to be plus s and plus s. This means that when we get to equilibrium, we will have 1 minus 2s. We will have s and s. So this is very much like a KSP type table. Any questions on that so far? Okay. So just like we would do with a KSP sort of reaction here, we're going to put this into our K expression, and it is going to be our products, which is this guy, times the chloride divided by our NH3, and we want to make sure we square it. And again, that's going to equal our combined K value of 2.4 times 10 to the minus 3. Putting in everything in here, because again, we do want to solve for S, right? Because S does equal the molar solubility. So we do kind of want to solve for S here. So putting that in, that gives us S times S divided by 1.0 minus 2s squared is equal to 2.4 times 10 to the minus 3. So here the goal again is to solve for s. So at this point, you could hopefully see it, but it is a perfect square on both sides. So we're going to square root both sides here. When we square root the left-hand side, that leaves us an s and a 1 minus 2s. On the right-hand side, I'm going to actually take the square root there, 2.4 to the minus 3. And that's going to give me something like 4 we'll call it 9 times 10 to the minus 2. I'm then going to multiply everything on the bottom to the right-hand side. So that's going to give me S is equal to 4.9 times 10 to the minus 2 minus 9.8 to the minus 2. S. Going to bring my S's to one side, and that's going to give me 1.098s is equal to 4.9 times 10 to the minus 2. And if I do that there, we're going to divide it to the other side. Going to give me an S of 4.5 times 10 to the minus 2 molar would be our silver chloride's solubility in what I got there? Yep, in ammonia. Any questions on that? So here you can see that you can sort of combo a couple of different Ks together and put them together again. Ultimately, all the Ks are really the same, no matter what it is. And you could treat them pretty much the same. Any questions on any of that calculation there? Just for sort of reference sake, just so you have an idea as to, is that it good or bad, that number, or is it more soluble in, say, ammonia than water? For comparison's sake, if we looked at silver chloride in water, like I think we did before. The KSP of silver chloride in water is 1.6 times 10 to the minus 10. That essentially would get us S squared is equal to 1.6 times 10 to the minus 10. That would get us a molar solubility for silver chloride of something like 1.3 times 10 to the minus 5 molar in water. I think we did this calculation earlier. Now, in ammonia, we have 4.5 times 10 to the minus 2 molar in NH3. So when we compare the solubility of something like silver chloride, which is that white solid that you make, in water versus in ammonia, we see that in ammonia, it is much, much more soluble than it is in the water. So it has a much higher sort of solubility in ammonia than it does in water. And what does that mean? That means that it's got something like, you know, thousands of times, 3,000 times more soluble in ammonia than it is in water. What that means is the formation of a complex ion, like it wants to do here, is really, really favored. And that's why we see such a large KF value, because the formation of a complex ion is always favored. We do see a much higher solubility of this silver in ammonia, which is a ligand, than versus water. In fact, when you do like that experiment I was talking about earlier, that qualitative analysis experiment, this is actually how you identify you have silver. You actually make the silver chloride solid. You add some ammonia to it, and it will make that complex ion. And that complex ion is aqueous. So it goes from solid to basically a solution. And then you add some more kind of acid to it and chloride, and you make the solid again. So you could actually have this silver chloride solid. You add some ammonia to it, it will basically all dissolve. You won't have any solid left. And that means that the ammonia, when it gets near something like silver, they have such a strong attraction to each other that they want to make that complex ion, which is why, again, we see the KF value being a large value for that in that case. Any questions on that? Any questions on complex ions or how to do them there? And just comparison, just for grams, if you want sort of a visualization of grams, in water, you could dissolve something like, I think, 0.00186 grams per liter, while in ammonia, you can dissolve something like 6.45 grams per liter. So you can see in ammonia, you could dissolve a tremendously more amount of silver chloride than you can, obviously, in water. In water, you could only dissolve basically, not even 0.01 grams. You could do about 6 grams of it in ammonia. So that's why it's very, very soluble in ammonia in this particular case. And it shows that whenever you have that opportunity or that situation where you can form a complex ion, definitely complex ions want to be formed because they have very strong attractions to each other. And that's why we see those really large values of KF. Any questions on that? Here is a table, I think, from your book of some KF values. And again, if you look at this table, as you can see, a lot of them are really, really large. So you got some to the 25th, you got some, to the 19, to the 10, to the 18, to the, time sent to the 23rd. So these are very, very large values of KF. And again, what that really means is, like I just mentioned, pretty much if you have that opportunity to make a complex ion, it is probably pretty favored to happen because there's just that strong attraction between those things. Any questions on anything in this chapter here? That actually does wrap up this chapter. Okay, so that is chapter 15, and that means that we will be having the exam again, not on Tuesdays. So the exam will be Thursday, I think. Gives you a week. And it will cover chapter 14 and 15. So that's all that fun stuff. So 14 is all the acids, the bases, the salts, the buffers, the titrations, and then chapter 15, which is our complex ions and our solubility. Any questions on any of that stuff? So we'll take it next Thursday during lab, like we've done before through proctorial. We'll maybe have a small lecture beforehand, and then we will take the exam on Thursday. All right. Any questions on exam? Any of that type of stuff happening? Okay. Then let us switch gears and talk about, let's see here. We talked about the first two parts. So part 3, I guess it is, or really kind of the second part of the buffer experiment. So give me 1 second here. I'll just get a clean page to write on. Okay. So in part 1, which encompasses basically part 1 and 2 of the written procedure there. So really part 1 and 2 we talked about last time. That's when you're going to basically make a buffer using what they refer to as method 1, I believe. And method 1 is essentially you're just going to kind of go into the shelf and you're basically just going to pick up your combination of a weak acid and conjugate base, or a weak base and a conjugate acid. And as we talked about last time, what you want to do is you want to make sure that you pick a combination where you have a pKa value that's close to your assigned pH. So everybody got an assigned pH for a buffer. You want to go through that list. Again, I think there's like a list of 6 of them, I want to say. And from that list of 6, you want to pick the proper pair, and you're going to basically make that buffer the way they asked you to. So I think in your cases, you think we're going to make like 100 milliliters of it, perhaps at some type of molarity that was given to you. And you want to make sure you make it that way. Now, the second way that we're going to basically make a buffer is by, in part 3, you're going to make the same buffer. So just so we're clear, the same buffer that you did for part 1 and part 2. But the way you're going to make it is actually different than how you made it in part 1. In part 1, like I said, you technically go to the shelf, you pick off both parts of the buffer, the acid part and the base part, and you want to basically dump it in. No, so again, when you're trying to pick a combination that is that's correct to choose for part 1 of an acid or a base, you just want one that has a pKa value that's basically plus or minus 1 of your assigned pH. So it doesn't have to be perfectly matched, but it needs to be usually plus or minus 1 of the pH you're trying to make. So usually like plus or minus 1 of the pH, the pKa value. And from that, you can make pretty much a suitable buffer if you pick a combination that's there. You don't have to necessarily find one that's exactly the same pH as yours. And that's why you have that sort of plus or minus 1 range. And you should usually be fine in that particular case. Now, in part 3, again, you're going to be making the same component, their same buffer. The only difference is you're going to make the buffer through a reaction. And that's what is sometimes referred to as making the buffer in situ, which means basically as a result of a chemical reaction. So at some point, you picked for part 1 a combination of a weak acid, probably, and a conjugate base, right? And what we're going to talk about here is we're just going to kind of use the numbers, I think, from their example in the introduction. So if we remember in the introduction, we wanted to make, I think it was 1 liter. We wanted to make a, what was that? It was like total 1 mole, I think there. We wanted to make a 1 liter of 1 molar. That made the numbers easy. So we wanted to make 1 liter of 1 molar buffer, if you remember. And what that gave us was a total of 1 moles, right? And that 1 moles was made up of both the acid part and the base part. And in our calculation from part 1 in our example here, I think we ended with 0.76 moles of our acid part that we needed and 0.24 moles of our base part. And these are the numbers that you would have from part 1's calculation. And if you remember, these are the numbers that you would use to figure out how much volume of the acid you should add or how much volume of the base you should have. So you actually should have these numbers from part 1 for part 3 calculation. So that should make it a little bit easier. And obviously these aren't the right numbers. You need to use your numbers. So let's say, for example, that I decided I wanted to make a buffer by reacting it with hydroxide, right? And let's say I want to make a reaction from taking my acid and I want to react it with a strong base like sodium hydroxide. And what we would get is some water and my conjugate base, right? Okay, so in this case, what we're going to do is we want to use only one component of our buffer. So in my case, I'm going to use just the acid. So I'm going to use the acid. I'm going to react it with the sodium hydroxide. And this I'm going to try to produce. So I'm not starting with any of my conjugate base here. I am going to try to make my conjugate base as a result of this chemical reaction. I not only want to make my conjugate base, but I want to make the right amount of my conjugate base so that when I am done, I will have this ratio still, this many moles of the acid and this many moles of the base, because that ratio I figured out in part 1 would give me the right pH for my buffer. Any questions on that so far? So the goal here is to do a chemical reaction with one part of your buffer and either a strong acid or a strong base. You could choose either one, strong acid or strong base. And the result of that reaction will leave you only the buffer left over. And that buffer should have the correct amounts of acid and base to give you the right pH. So how we're going to do this is we would do an ice table. And again, here we are starting with 1 mole of this guy. And I am starting with 0 moles of this guy. Now, I'm just going to kind of do x's for now. So minus x, plus x, right? And for now, we'll call the base x. Right? which means when I reach equilibrium, 1 minus x, this will be 0, and I should be left with x. And at this particular point, that would be a good ice table, because what I am left with is a weak acid and a conjugate base, and I do not have any more strong base there. And I have just made a buffer. Any questions up to that point? So the goal here is, in your reaction, you need to get rid of all of the strong acid or strong base. So in my case, the base needs to be used up completely. So if I go back through this, the one thing that I do know is my base in my buffer, my conjugate base, should end up being 0.24 moles. So I know that when I get down here, this number should be 0.24 moles, which is good because that is what x would equal, which means it would be this x, it would also be this x, it would be this x, and it would be this x, which means I would technically have 1.0 minus 0.24, which would give me 0.76 moles, which is good because that's what I needed in terms of that. And that x would equal all those x's, including this x right here. And that x right there is 0.24 moles of my sodium hydroxide, which means if my molarity of my sodium hydroxide was, say, 1 molar in this made up example, I would now know that I need 0.24 moles of sodium hydroxide. My molarity is 1 mole per liter. The moles would cancel. That would tell me that I need 0.24 liters of sodium hydroxide, which means I would need to add 240 milliliters in my made up example here of sodium hydroxide to do that. So what you're going to have to do is, hopefully from part 1, you figured out what combination of a weak acid and conjugate base or a weak base and conjugate acid that you need to make your buffer. You also should have figured out from part 1 the moles of the acid that you need from your buffer and the moles of the base that you need from your buffer. And you could use those to figure out the moles that you actually need to end up with in part 3. So really those moles are your equilibrium moles. And as you can see from this example, you could kind of work your way backwards to figure out how much moles of either the acid or base, sodium hydroxide or HCl, you need to add to make your buffer as a result of this reaction. Any questions on any part of that? Okay, so part of part 3 is that. And again, you can do method 2. And again, you might want to read through the introduction again to look over that, what we just talked about here. But you really can choose either part, whatever part you want to do there. You could either choose the acid part or the base part of your buffer. And the goal here is to use just one part of your buffer and react it with either HCl, which is a strong acid, or react it with sodium hydroxide, which is a strong base. And you need to react it in a way that all of the strong acid and all of the strong base gets completely used up, and you don't have any of it left over when it's all said and done. And that the only thing that you have left over is your weak acid and conjugate base to make your buffer. So that's part of part 3. Any questions on that part of it? Okay. Now there's a second type of calculation that you need to do, is after you have successfully made this buffer here in part 3, which technically speaking should essentially be the same buffer as part 1. It's just going to be made differently, but you should end up with really the same buffer at the same desired pH. You're then going to take that buffer and pour 50 milliliters of your buffer into 2 different beakers. So once you've made your buffer through method 2, you will then split your buffer into 2 50 milliliter portions. So again, I think you're going to originally make 100 milliliters of buffer. You're basically going to split it in half, yes? And what you're going to do is to one of them, you're going to add 0.1 molar HCl. To the other one, you're going to add 0.1 molar sodium hydroxide. Now, your goal is to the beaker, we'll call this beaker 1, and this beaker 2. To the beaker 1, where you add the HCl, your goal is to make the pH change by 0.15 pH units. So what does that mean? That means, for example, if your buffer started at a pH of 5, when you add the acid, you hopefully should know, right? If you add an acid, the pH should go down, yes? So it should go down by 0.15 units, which means after you add your acid, you want the pH of this solution, in my example, to be 4.85. The goal is to figure out how much you need to add. So how many milliliters of HCl should you add to get your buffer to drop 0.15 pH units down? And then what you would do is over here, your goal is to get the pH to change by 0.1 pH units, which again means that if your buffer started at a pH of 5, after you add the sodium hydroxide, you want the buffer's pH to end up being 5.10. So you need to figure out how many milliliters of this guy you need to add to make it do that. So this is going to require some calculations and some thoughts about how you can do that. And there actually are a couple of different ways you could do that. I'm just going to give you some broad explanation of it. And I'm going to let you try to obviously figure it out yourself without me just telling you how to do it. But what you want to figure out is one way, and there's again a couple different ways or approaches that you could do, but perhaps one good way would be to do like a ice table, perhaps. Yeah. So you take your acid and perhaps you added your sodium hydroxide, gives you your NaA plus some H2O. And what you will know is initially you would have the moles of this in your buffer in your 50 milliliters. You would also have moles of this guy in your 50 milliliters. And the goal here is to basically use up all of our sodium hydroxide here, right? So what do we know about our sodium hydroxide? We know that it is 0.1 molar. And that is actually moles per liter, right? So when we would do a nice table like this, we would typically do this in terms of moles, which means this guy's in moles because you have that number. This guy's in moles, you have that number. This guy is not in moles. So technically we need to multiply this maybe by X. And what X would represent in this case is, in order to get me moles, X would equal liters. and X would represent the liters of sodium hydroxide I would need to add to get me moles. So you could kind of combine this into something like 0.1x. And what we do know is this is a buffer, so it should use up all of our sodium hydroxide. So the change here should be something like 0.1x, 0.1x plus 0.1x. Which means at equilibrium, you'll have your moles minus 0.1x. This should be zeroed out, and this would be 0.1, your moles plus 0.1x. At this point, you need to do some math. We would still have a buffer left over at this point. And when we think about a buffer, we should think about what equation? We should think about our Henderson-Hasselbalch equation, yeah? So you would now have this, and you would now have this, which would go into these places. You have your pKa, which is the same as part 1, and you could put your adjusted pH into here, either up or down. And once you do all that in some very careful math, I would say some very careful math, people always screw it up. Yes, so take your time with the math part here. Once you do, you might want to solve for X. And when you do, X will equal the liters. If we follow it all the way back, the liters of sodium hydroxide you would need to add in this particular example. You then can convert it to something like how many milliliters that would be in that particular case. You then want to do kind of the same calculation involving adding the acid to your buffer and figure out how much volume of HCl you would need to add. Any questions on that? All right, so that's just a kind of overview there, and that should hopefully put you in the right direction on this calculations. So part 3 here, there's a number of calculations, just so everybody's clear. You need to do a calculation of how you're going to make your buffer using method 2. And again, a reminder that the buffer is the same as in terms of the pH, molarity, and everything as what you made in part 1. And once you've now figured out how you're going to make that buffer, you then need to figure out you're going to take 50 milliliters of that buffer. So that changes some volume. So you want to think about that as well. So that changes some volume, and you want to basically do an ice table like I just kind of showed you there and figure out how much volume, how many milliliters of sodium hydroxide you would need to add to raise the pH of your buffer by 0.10 pH units. And then you would want to do a calculation to figure out how much HCl you would need to add to lower your pH of your buffer by 0.15 units. So those are the calculations that you need to do. You need to show the calculations, and you do need to, I believe, upload those calculations and